Perhaps we can start with the next talk. So we have to have Sakura telling us about, well,
Symmetries.
on symmetry.
So thank you very much. Thanks very much for having me here at the occasion of Hiroshi's birthday. And like many of the other speakers, I'm deeply indebted to you for support throughout my career. So happy birthday. I chose a cake. So I think everyone had a slightly different cake. Mine has lots of fruit and it's made in Germany. So my journey sort of starts in 2002. I think that's when I first met you.
You're a graduate student.
I was a graduate student at Cambridge, and you came for strings 2002, indicated by the Newton-Apple unraveling in strings, to the CMS in Cambridge. And I had been reading, so being a student of Peter Goddard and Matthias Gabriel, I was reading CFT papers, boundary CFT, and the paper actually was already mentioned, I think, by someone earlier, the Uri Olsen Yin paper on boundary states and collapse. So that was sort of my starting point. And you came to the registration desk, and we were like big-eyed students, and you came and talked to us and how it was. So that was the beginning. Then it continued 2006, when I actually had the fantastic opportunity to come to Caltech and be a postdoc there for 3 years. And this was the view out of my office. And it wasn't just taking nice pictures, but there was actually a lot of work being done in this slightly chaotic place. We saw graduate student offices from J1, where's J1, and I think you showed your office. This was my office. And it was really a truly inspiring environment because the group of postdocs and faculty and who you called in to actually be there really made a huge difference. And actually connected me to when Cumrun and his group started F-theory, we actually got on board with that, and you gave us sort of the freedom to do what we wanted. And I think that was fantastic. I also have a prefab. I can use a picture. I really think in the 2000s, the skills of taking pictures really was very limited. Sorry, so this is in the prefab at IPMU, the first F-theory meeting, which Taiwan organized. And this is the collaborative. And this is the back of Sheldon Katz. You will get more pictures like this. But then that actually, the series that was started at IPMU was then continued at Caltech. And here's actually a picture of Hiroshi at the FDR meeting at Caltech. And again, the back of illustrious people's heads. I think this is Mike Clem. This is Dave Morrison. Obviously, that's John Schwartz, and that's you. Sorry, this is
Right?
Yes. Anyway, so one of these things, a lot of things have been said already. One thing that hasn't been mentioned, if you were at Caltech in 2006, this was a very dominant thing, and I think all the postdocs and students who were there at the time with me can back up from this, that Hiroshi was zipping around the campus and in 2006, that was not a very common sight for someone to use this as modal transport. But of course, that in 2022, this is where we are, right? London, Paris, New York, you go Pisa, you go wherever you want, everyone is using this. So clearly, there's a lot of trend setting going on that we are not aware of.
Yeah, my wasn't electric.
Okay, the real question, and that's something I was discussing with John Schwartz and Aspen in the summer, is how do you manage to get it all done in the 24 hours that you're all given? And really, in terms of sort of just the sheer volume of things that you manage to do and excel in, I think it would be amazing if we could sort of do, at least I would be fantastically happy to do a fraction of that. Beyond just the research leadership, of course, you're an author, you're a science educator, a movie advisor, and a really wonderful leader in all these institutions. So here at IPMU, the Aspen Physics Center, you continue to be really, supportive and leading figure, of course, in Caltech. So I think we're all indebted to you for the support throughout the science development and fostering this field. So in terms of research, I think to me what came to mind was that Hiroshi's research is really very broad, like in terms of where the impact was. It's not just in one particular thing, it's in a lot of different things. So it's in CFTs, string theory, generally quantum gravity, holography, and mathematics. And so basically what I will try to do is to aspire to bring a little bit of all of these things in. So symmetries are a pretty good starting point for this. They are central to quantum field theories, to holography, to quantum gravity. We've heard many sort of mentions of that for some gravity, and also, of course, as we'll see, to mathematics. And my instance here more topology or category theory. So this comes with a nice pitch. The goal is to get all of these ideas together. Anyway, the starting point is that really in 2022, we think of symmetries in quantum field theories as topological defects. And perhaps really far from the initial, at least to me, this is the initial inception of this idea by Noether in 1918, received a paper and Göttingen about deviation type symmetries. Actually, about Noether, there's some fun fact. She had also in March this year her birthday. So in 10 years, we won't be having again nice birthday. So it's maybe something to keep in mind. Anyway, so what is the idea here? We have some point-like object that is charged under symmetry, which is what we would call nowadays a zero-form symmetry. And you can measure that by surrounding it with a topological operator and measure the charge of that.
What does this shell mean?
Yeah, so that's actually coming, so it's somewhere here.
Okay, well,
It's coming from Lie. And in the German, it's like the possessive pronoun, the Lie type symmetry. And it also means, so Lieschen is a small version of the name Lisa. So it's actually for German a pretty hilarious, that's why nobody else is German. So the joke is lost. Anyway. So let me now dive in and discuss a little bit what has been happening in the realm of symmetries. I think at IPMU is like preaching to the prophets, bringing codes to Newcastle, but let me do it anyway. So what actually has been happening in the last couple of years is there's been an explosion of symmetries, and starting, of course, with the higher form symmetries in 2014, where, so generalizing this picture I was drawing here to operators that are not point-like standard operators, so p-dimensional charge defects, whose charge can be measured by surrounding them with a topological operator of codimension p+1. And they generate the so-called p-form symmetry. And we think of these as these sort of extended objects, we can fuse them. And in fact, the assumption at this point here is that they're labeled by some group labels G and H, and they satisfy the group multiplication law. So this is what we would call a group-like p-form symmetry. And just like with zero forms, they couple to background fields, which in this case are, okay, so here, this should be gamma p, excuse me. They actually can be discrete or finite groups. So these are usually valid in this kind of cohort. So the p+1 form fields, the background fields of these symmetries. If you have a theory that has multiple such higher symmetries, you can ask, are they all independent? And the sort of simplest instance when they're not is when you have a higher group. So for example, you have a zero form symmetry, so something just like what we saw in this example, and then also right form symmetry, and you can form what's called a two group. So what it means is that essentially these two types of symmetry generators are not independent, but actually have some relation. Here, the relation is that actually the background for the one form symmetry is not closed, but given in terms of some function. The background for the zero form symmetry. We don't need it. We have to give some more concrete examples later. again, in this case, we're assuming everything is invertible, so it's satisfies group one, except for the backgrounds and not necessarily independent. So what actually happened in the last bit over here is that we relaxed this assumption that the diffusion of these topological defects is invertible, so it's group one. So we have two of these defects. If you use them together, and the assumption God gives you another one labeled by the product of two elements in the group, but actually can be more generally some kind of some sum over the topological defects of this dimension. Of course, if you look at this sort of equation and you come from two dimensions, this is very well known, looking at, for example, Lambda lines and two-dimensional natural conformal theories, and to some extent to condensata theories in three dimensions, but in D bigger than 3, so space on dimension bigger than 3, this is actually something that doesn't exist with the variation. So if you have these p-dimensional topological defects that then don't obey this group-like thing that they're non-invertible, then you can ask, well, what is the most general thing that we could think of that actually exists, perhaps in some kind of field theory? Well, then we say it could be, the collection of all such defects, so of dimension 0 until d minus 1, where d is the dimension of the quantum field theory, and all of them could have some complicated fusions that are not invertible. And once you sort of think about what the full structure should be, it should be something that a mathematician would call a higher fusion. And that's sort of maybe where we've landed, and we need to understand these things. The main surprise is that these type, at least to me, the surprise is that these type of symmetries occur not just in very obscure theories that you might not have thought about, but actually occurring in really vanilla Engels theories in 3D, 4D, 5D. So this is actually something that I think we should have known. Okay, so there's been a lot of activity just in QFT. I tried to list of all the papers that I've been reading in the last year or so. A lot of people are here at IPMU, in particular, Yuchi and Heidi Mori and Zing. And so lots of people, and this is not mentioning the people that I observed, and there's been lots of activity. What I'd like to do today is give you some sort of idea how to construct such non-invertible symmetries and to package them and formulate this in terms of categorical language. And that's just sort of from a quantum field theory perspective. And then I'll define something like a symmetry category and symmetry category webs. I'll explain what that is. And it's a very natural concept if you've thought about different global forms like H groups, like SO versus string versus FS and so on. And then the third point I'll discuss, well, how all these things actually would have a natural occurrence in string theory or holography. So that's on time back to sort of things that she usually talked about before, things that actually very ritual from the feeling of the interaction of string theory. So a lot of things that we've learned in string theory lectures will have a reappearance in terms of these symmetry structures. So the work I'll talk about is done in collaboration with these fantastic people. Lakshya Bhardwaj is a postdoc in Oxford, and Jing Jiang, who is also a postdoc in Oxford. Leah Albertine is my student, and there's Apoorv Tiwari, who is a condensed matter theorist in Stockholm, and then all the friends, Javier Buzzi, Ibu Ba, and Federico Valenti in these collection of papers.
Twice.
Yes, because it's a collection of papers, but also he works double. I should call him. Anyway, so I just to give you a little bit an idea of what these symmetry categories are, and to give you a sense of why this is difficult. It's actually, we are saying, take a d-dimensional QFT, and then look at all the set of topological defects of dimension Q from 0 to d minus 1, and then we can say, well, this forms what formally would be called a d minus 1 category. What is category has objects, and then the morphisms. In a higher category, you get morphisms between morphisms and morphisms between those two morphisms, and so on and so forth until you sort of come in. So the objects here are the top dimensional topological defects. And then the one morphisms are basically between these. So the one dimensional is, and the morphisms are between the top dimensional defect of these objects. and so on and so forth. And so you generally be looking at things like that. So you have, say, a surface defect, you have a line defect, a local operator, and then there's another line operator. And these things can form very complicated structures. And now there's a question, if you would like to have something like fusion, which you would like, and what type of mathematical structure is that? And that's a fusion, higher fusion category. Now in mathematics, in fact, to my knowledge, sort of formal definition, the satisfactory also knows is actually only existent when higher is actually 2. So that's somewhat limited, but and that's very nicely written out in this paper by Chris Douglas and Gabriel John. So the question is, can the math people, can mathematicians actually develop this further? And there's a lot of work that actually is going on very much in sync with what we're doing. But the approach I'll take today is not sort of hit you with a lot of category theory, try to sort of motivate it from a physics. So in 2 dimensions, so basically the approach we'll be taking is a sort of generalized notion of gauging. So if you know Albrecht folding, that's sort of generalized notion of constructions. And indeed, in 2 dimensions, it goes back a while, motivated by this group of people, Winkler, Schreiber, Cargill, in 2D theories, where they were doing sort of gauging fusion line categories. And also this paper has now really gotten a lot of traction by Laksha and Eugene, which I think was written here for KU. So this is sort of the starting point of the idea, but then it's generalized in 3D. There's by Peschling and Fratkin. And then basically what I'd like to discuss is these higher dimensional cases that go beyond this. And they're sort of motivated by various different approaches that are overlapping. And one is this KOZ approach here, which I'll discuss later on in a little bit more detail, based on mixed anomalies and quantum field theories, from which we get non-invertible symmetries. There are also the constructions of duality defects. And then the thing that I'll focus on most is this gauging homomorphisms. So I'll give some examples here. So for instance, we could start with the spin for Young-Mills theory. Essentially in any dimension, this has an outer automorphism that changes the 2 legs of the linear diagram, so that's outer automorphisms in 2. And we can gauge that and get the pin +1 theory. And that actually will have non-invertible symmetry. You can also gauge charge conjugation in Young-Mills theory, like O2 or SUN tilde theories, but there's also gaugings, of course, of, for example, spin 8 with some non-abelian flips like S3 in that case. So these things can be studied essentially in any dimension using various methods. Okay. So as a warm-up, I'd just like to sort of discuss a little bit how this gauging in standard categories works. The way we should think about this is just this construction of non-invertible symmetries, but focusing on topological line operators. So we can, for example, take a three-dimensional common field theory, think of it as the Cumrun Vafa gauge theory, if you like, and then it has a finite zero-form symmetry generated now by topological defect, the surface defect. And now I'd like to ask, that theory has a set of topological lines, and now I act with the symmetry, the zero-form symmetry on the set of topological lines, and it gives another set of topological lines in the gauge theory. Now, what is that category C sub G of lines of the gauging? So objects in that category fall into 2 classes. The first one is you just take the gauge invariant combinations of the lines of the theory before. To get the most natural symmetry that is related by orbits called G. And so it's just a combination of topological lines in these orbits. But there's more. And the sort of mathematical way of characterizing that is you get also topological lines as a dual to this zero-form symmetry U2G. And basically, these lines form a subcategory, which is the representation category for G. So this is sort of a little bit, I'm introducing these representation categories, and they don't have true representation category. There's a very nice physical way of thinking things. Namely, if you have a theory and has a symmetry G, then I can sort of stack on top of this a one-dimensional TQ of T. with symmetry G. And it's just a sort of, I have this theory, and I just take the product with this 1D TQFT that is protected by the symmetry G. And then the gauging, I'm doing it, and gauging sort of now the diagonal of the symmetry G on this TQFT and the theory T. And then what happens is that this 1D G TQFT actually becomes sort of not decoupled, but it's a part of this gauge theory. It becomes a topological defect in that. And so in this way, so this sort of notion of somewhat generalized gauging, which in higher dimensions will become relevant, is related to what you may have heard in terms of generalization defects. So this is essentially the second class of ways of getting additional line defects. And there are also mixtures between these two that are labeled essentially by stabilizer groups or objects in these orbits. And you can direct these with some representations of the this is finding more complicated thing, but then you should remember these two types of shortened. Now, between these, so that case, they're just point-like and topological operators are again either gene-invariant combinations of morphisms in the initial category, so they're just gene-invariant topological local operators, or they're actually morphisms in this representation of G category. So they're zero-dimensional interfaces between line and TQFTs. Of course, when you're talking about non-invertible symmetries, we'd like to know how to calculate fusions. In this case, fusions of lines. And so the fusions actually either just the fusions of representations of G, D1R, D1R prime, the D1R tends to R prime, or they can be mixed fusions. So a little bit harder in terms of these kind of stabilizers. Anyway, so this is slightly more technical point. Let me go to the example. So for this 3D spin foreign theory, we're saying there's this Z2 zero form homomorphism. It acts on the one form symmetry, which in this case is Z2 times Z2. It's exchanging these two factors. Here I'm labeling this by Z2S and Z2C. There's also the diagonal, which I'll call Z2B, which of course is independent. So what this uniform symmetry does is it exchanges these two. And so before we gauge in this category for the spin for n theory, the line objects are basically, there's a trivial line, there's the S, the C, and the V line, and the S and C basically fused to the V line. So that's the whole structure. And these are all invertibles of D1S squared is there. So in React, it exchanges these two, and V is invariant, and that gives us the spin for n theory. And now we can just apply this general method to construct the gauge theory. The way you think about this is basically this D1S line, when it pierces this generator for this zero form symmetry, transforms into a D1C line. And now we would like to just gauge this together. So again, the objects are essentially the invariant combinations. So in this case, this is the sum D1S plus D1C, as well as D1B. D1H, so this one has a trivial stabilizer, this one is non-trivial stabilizer. Then there are these topological lines that come from the dual of the zero form symmetry. They form this rep Z2. I'll call these D1 minus. The D1 minus is the generator of the dual to the zero form symmetry. And then there are combinations of essentially can combine the D1 minus with the really. And so the object in this new category. So what we'd like to see is what actually the fusions of the particular DSD1FC. So to calculate the fusion that's used would actually first observe what actually is the fusion in the pre-gauge category. So I can model this, the D1SC is just D1S plus C. We know the fusion in the spin for n. So this just gives us D1SC. But to actually make sure that this also is the correct fusion in the resulting in the gauge category, we need to look at what happens to the morphisms. So actually what happens at the junctions and how do they transform under this. So in particular, I can have this morphism from D1SC, D1B to D1SC. And I'd like to know actually what's sort of the structure of the Z2 action on these morphisms. So the two morphisms that basically come from S tensor C into B and C tensor S into B. In fact, under the Z2, they're exchanged into each other. So in fact, when we decompose them in the Z2 action, it's a two-dimensional space with morphisms that decompose plus and minus. So in fact, what we'll find from this is that essentially both of these, both the D1SC fuses with D1V to D1C, but also the one that is dressed with this D1 minus one is actually fusing the D1SC. So there's actually this sort of putative thing over here is actually true also in the H category. Okay, now similarly, which is maybe slightly more interesting, we can calculate the fusion, the C minus itself, and what you find at the end of this is the sum of all the other lines. And so if you actually look at this here, this is now sort of very obviously non-invertible, that you get the product of two of these topological lines gives the sum of all the other lines. And so when you put them together, you actually get precisely what's called the Cumrun types into the two category. And in fact, in this case, you can put this all together and you form a set of lines that is given class prime theory form the representation category of T8. Okay, so that's with topological lines. Now, what we'd really like to do is generalize this to higher dimensional topological objects. And the next one is, of course, so what would go under the name of fusion 2 categories. So here, the objects are now two-dimensional topological surfaces. So if they're invertible, they would form sort of generators of a D-3 form symmetry. The one morphisms, the lines, so we've discussed the layer from one morphism to morphisms. Now we're adding this layer of surfaces. And there'll be a fusion now of these surfaces. So we stack these things together and we get another object. Here, on this side here, another surface. But then also on each surface, we can have sort of joint morphisms. So the one morphism here is basically this line here, and then the two morphisms is this point line before. Right here between your one morphism D1 will be to the D1 and D5. So this structure already has the layers of surfaces, lines, and local operators. And what we'd like to now see is what actually is the structure of this, the rules of the game. So to actually get an example of two category that acts on a form of theory, you can start with some fusion 2 category with a symmetry C that has again a zero form symmetry acting on it, and the starting point is invertible. The nice thing about starting with something that's invertible is that you then actually know what all the fusions are, and then you have to construct a consistently gauging this zero form solution. So the starting point is relatively simple. We have the objects, topological surfaces generated, they're generating the D-3 form symmetry in this case, topological lines, they're also invertible, they're local operators. And now what we'd like to do is gauge a zero form symmetry that acts on this complete set of on this full 2 category. So we've already learned from this warm-up example of the 1 category that in fact on the objects here we should have 2 types of contributions. One is the G-invariant object, again, just take the surfaces, take invariant combinations. And then there's also this contribution that in the 1 category case was the rep G contribution. Here this becomes the 2 rep G. That's something that you could call the 2 representation category. And just because you're physicists at heart, we can just think of it in a much more intuitive way. And it's just a realization of a generalized type of gauging. So the way to actually think about this is, as I explained earlier, think of the theory, and now we can take sort of product with a 2D TQ of T that's protected by by the same symmetry G, and then gauge this diagonal symmetry T. And then this becomes actually a total the surface defect in the gauge theory. And so that's basically a real tool. Much more generally, we can sort of take any theory T, so in any gauging of some higher form symmetry, can take any theory T, which has some gamma P form symmetry, add to it a P plus 1 dimensional symmetry protected topological theory, and then gauge that symmetry, the diagonal symmetry. And then this SPT here will contribute actually a topological defect in the gauge theory. And so that's all the general principle, and capitalize that situation. So in light of this, we can revisit the three-dimensional spin for n-gauge theory. So we've now talked about this several times. So maybe quick about the basics. There's the one-form symmetry, there's the zero-form symmetry, and the zero-form symmetry acts on one-form symmetry. And so really, in fact, I was a bit sort of not completely straight with you about this. What you really have here is not just the zero-form symmetry and one-form symmetry. You technically have what's called the split two group. So what this means is just that the zero-form symmetry really acts on one-form symmetry. And so in fact, these two things form the two group, which is sort of like a secondary product between zero-form symmetry and one-form. In terms of the background fields, so B2 here is the background for this diagonalizing two. What it means is that there's some couples again in terms of the background of the zero form and the other combination of the one-form symmetry. So in fact, if you repeat this whole structure that I just explained for the two category case, the resulting the actual spin for n symmetry category is the two vec. So these are the two vector spaces of the two group. And so this contains in particular the two vector space for Z2, the two vector Z2, but also the two vector Z2 squared. This part here. Anyway, so we can now gauge what it means is gauge as into zero form, and then the resulting categories, in fact, the two vector of this extension group. So here the hat indicates just a contracting dual group. So for gamma one, this is just Z2 minus Z2, but now with this action, it's given in terms of this split two group. So in terms of this, and that's the gamma 0 to out. Okay, so how many time for one?
Yeah, till the four.
Point is that we gauge, we get this two of this 0 symmetry. To see that, in fact, there's a neat way of this. We can first actually start with the theory and find gauge and one-form symmetry. Then everything actually is in terms of just the zero-form symmetries, and then the category is just two like of the zero-form symmetry, and then we can gauge the full zero-form symmetry and make use of the true. In this case, like in point theory, just the Z8 group which is gamma symmetry. So just to give you an overview of what the field is doing here, the three-dimensional, if you have this SO4N algebra, we can look at the spin 4N theory. This has the symmetry category, which is given in terms of two vector people. Then we gauge the zero-form symmetry, and we went to pin plus, and then we get this two vector D8, and this is non-invertible. So it is non-invertible, and it contains also, of course, the one vector D8 that I constructed at the beginning. You can go back, just gauge sort of back, but you can also, of course, gauge to PSO by gauging the full Vafa symmetry. And in that case, you get sort of the two back of this blue D8. And then you can also go all the way here. This is basically the last step. This is or you can gauge and go to PO. And in this case, you also get a non-invertible symmetry. And of course, you can now go wild, and there are also partial gaugings and the whole. What I call these kind of things is basically categorical symmetry, because you start with a category. In this case, you know everything about this category, and then by gauging, you can reach all these other global forms of your gauge group and the associated symmetry categories. Now, of course, what we've basically done, we can repeat in higher dimensions, except that now these are higher dimensions, higher pseudo fusion categories. So you get in D dimensions, the D minus one break this two group, and here's a D minus one, and so on and so forth. So from us, it actually isn't, these are relatively simple enough categories. We don't really need a full mathematical description of the higher categories, higher than two, but it will sort of gives you an idea of just constructively how all these categories fit together. And of course, once you have this picture, you can ask yourself, is there sort of a way of, without starting at one point and engaging to reach all this, there's some way of actually characterizing some more universal object that then gives you sort of by all these different global forms and their categories. And indeed, that's mathematical object that's known as the Greenfield center, and in physics, this now has been going by the name of the symmetry theory of symmetry TFT. So what is this mathematical? If you have an n category, you have this black of different categories that give you the symmetry structures for field theories. You can think of these as generalizing the sort of notion of different global forms of the gauge theory. Mathematically, it's manifested by saying all these categories, those n categories in a given web, they share the same Greenfield center. So in 2 dimensions, this is extremely well known. And if you have a fusion category C, there's a 3-dimensional TQFT, the True theory TEC, that characterizes essentially the set of all lines of the Greenfield center, is actually characterized as the 2D theories that can live on a boundary. So this Greenfield center theory, you should think of as a theory characterizing a theory or its lines, and its topological defects in 1-dimensional pair. And there's a sort of long history in convex matter and mathematics studying these particular theories. And some recent work by Cumrun, where this C is exactly one of these non-invertible categories. But then the bigger than 2, really they should be generating exactly these types of symmetry webs. And so what you're looking for is what are the sort of D plus 1-dimensional theories which actually would give rise to the same, all these symmetry categories essentially come from this one category in 1-dimensional. And so this one has to compute the Greenfield center for these higher frequency categories. Not everyone here is a friend of categories. I think I've already said the word category now, I don't know, counted maybe 100 times. Some of you are QFT practitioners, string theorists, holographers, being sort of connected to actually the word. And what is this is basically what we now call symmetry TFT. I want to now sort of switch gear a little bit and forget about the categories, and now talk a little bit about what that picture that I was just sort of sketching has to do with things that I know really well in string theory. So just as a very brief recap, if you have a theory T in the dimensions with some global symmetries, the top anomaly can be captured in terms of precisely these background fields, which are P forms. And essentially what it means is you look at the partition function and you do a background gauge field transformation, and the partition function picks up some phase, and then the space can interpret it as the partition function of the theory, which is a theory that was in 1-dimensional. And also has, say, the symmetry that's characterizing the characters of this background. So in the last sort of, well, going back to Fried and Telemann, and then some lower dimensional work by Gayol and these recent papers here, really what this describes is the symmetry. What can be described in this way is the symmetry TFT, or the sandwich. I was thinking what would be the Japanese analog of the sandwich. I don't know, but maybe the Castella cake. The symmetry TFT is a D plus 1-dimensional topological theory, which admits some gap boundary condition. And we should think of the anomaly theory as basically being participating here. This is the gap boundary condition, the topological boundary condition. This is the symmetry TFT, and this is sort of physical non-topological boundary condition. And the actual theory coupled to the anomalies is obtained by sort of collapsing this part of the sandwich real cake. And so by choosing different boundary conditions here, you can generate different rules. So what you should think about this Greenfield center series, it lives here somewhere, and it generates all these different topological objects that you're looking for, and then imposing different boundary conditions results in symmetry categories for the physical theory. So, and I think you were saying this in one talk earlier. Well, we know examples of this, of course, very quickly. The classic example for some TFT is basically this topological coupling that we know in ADS5 that just sort of comes in the ADS5 space-time after we integrate over the 5-sphere and units of flux. We get a coupling B2 DC2. B2 and C2 already, MS and S and all background fields. And by using boundary conditions on these, we generate different global forms of the dual gauge theory. In this case, the chemical source of numbers. That was already noted by written in 1998, so it's not anything new. But we can reinterpret this in terms of now think about these symmetry of these, where we can impose these boundaries. And of course, we can also construct in from here the generators of the symmetry and also the charged objects. So the Wilson lines and the Toft lines are obtained by taking, so say for example, beta it will be 2 over 2 minus and 2 manifolds, and then depending on whether they have Dirichlet and Riemann boundary conditions, become the charge or charged objects under these symmetries. Okay, so there are two things that we've noticed in the last year which connect to this picture. So how does the symmetry actually come about in string theory and holography? Two observations. The first one is if you do geometric engineering, so you compactify string theory on some non-compact singular space like a Calabi-Yau or a G2, and you engineer a quantum field theory in d dimensions, so call it T of X, where X is that complexification space. And in fact, you can reduce also the topological couplings in string theory and M theory in your 11 on 10 dimensions. Now, on the boundary of this, so the boundary is a compact space, and the resulting theory lives in D plus 1 dimensions. And that theory is actually the symmetry of this quantum field theory that you generally mentioned. So that's sort of something we've tested in many instances and gives sort of a string theoretic derivation of these symmetry ethics. The other one is holography, connection holography. There's, of course, the illustration that goes back to 98. There were also papers by Luigi, Gabi, and Oren Bergman in the ADS4. But in fact, there's a similar philosophy that if you take the bulk topological couplings in the ADS D plus 1, or if you're doing not conformal holography, like for example, Schafer-Nameki, then in fact, these bulk topological couplings are furnishing also the symmetry. So they give you all the information that you need to construct so the symmetry structure of the boundary. So there's a huge amount of evidence that in fact using this approach can also construct not only invertible things, like in this an example here, like this would just give us the N1 form symmetries. But in fact, here we can also now construct the non-invertible symmetries in holography. So I want to discuss this very briefly in the context of this Klebanov-Strassler setup. And that's particularly interesting because here there's utility to these symmetries. So in fact, so far I was just discussing a lot of mathematical structure, and in this particular setting, these higher form symmetries really have some physics capture, right? So it's some of the most interesting one to consider. So what is the setup? It's a very old kind of solution in supergravity. Well, we're looking at these three branes probing a canonical singularity, in this case, the cone over T11. So it's a particular Calabi-Yau singularity. And we're looking at the 2B solution, it's A is 5 times T1 with 5 form flux. So that's conform. So there's definitely nothing interesting in terms of, confinement or anything, but once you're actually wrapping addition 5 branes on the T11, so T11 topologically is just this is like the Einstein space, just topologically as 3 times S2, and have the 5s on S2, and induces flux on the sphere, m units of flux, and in fact that breaks the conformal invariant, and we get conjecture in our holographic solution that isn't dual to conformal field theory, but to conjecturally the n equals 1 pure Young-Mills theory with SUM gauge algebra. So it's actually dual to a cascade of gauge theories with n equals 1 supersymmetry. There's a cascade of cyber properties, and at the end, if you choose M and N to be sort of multiples of the integer multiples, so you get SUM equals 1 to the others. There's a radial direction, and there's a T11, and then there's fluxes. But really, you should think of this radial direction as the slow direction. Now, this data, the solution itself doesn't actually specify anything about the global form of the gauge theory. So this is sort of not specified before you say anything about the topological couplings. It's surprisingly something that hasn't been done back in the day, because of course all these symmetry considerations in a play. If I go to the holographic description, in fact, let me put a very quick interlude on these non-invertibles before the n equals 1 to the angles. So we know that as to m pure n equals 1 to the angle, so if m confined vacuum and infrared, it has exact symmetry, which is the one-form symmetry. So the question is what happens actually in PS? And so in fact, to go from SUM to PSUM, we gauge the center symmetry, and in fact, what we'll see is that will result in some non-invertible stuff. So where does the non-invertible symmetry come from? Well, for the angles 1 SUM, actually it doesn't just have a one-form symmetry, it also has this zero form Z2M chiral symmetry. And that gives a vertical under Z2. So there's M combining that come from. And we see that there's a background flow again, and actually there's a mixed anomaly between this chiral symmetry and the one-form symmetry. And so the anomaly is basically the background for the zero form and contains the one-form symmetry. And so if you look at this particular anomaly, that's actually what I would call a KOZ applicable setup. So as in this paper, and Kage Morizing to show the construction, how when you have a mixed and tough anomaly of this sort of type, then in fact you can get a non-inverted symmetry for this, for basically in this case, for non-inverted symmetry, and gauging now one-form symmetry. So how to see that actually there's something maybe not quite kosher about the zero form symmetry generator. All we need to do is just write down sort of a background gauge transformation acting on this zero form symmetry generator, D3 on some 3 manifold. Because of this mixed anomaly, it will transform with exactly this Poincaré square root 2 kind of transform. But this actually in itself not a really good you got the topological operator, and we can't gauge how the one-form symmetry. But what the observation was, we can actually stack this with some TQFT that cancels this anomaly. So in this case, if there's some TQFTs, if it's one and left, TQFTs is just Chern-Simons theory, but it cancels this anomaly. So if we actually take this product, then the resulting defect is in fact perfectly fine. We can gauge the one-form symmetry, and the fusion dictated essentially by the fusion of this U1M theory tells us for SUM, this zero form symmetry defect is now non-invertible. So it sort of fuses to basically this two generator, and so the two is literally the label in this as M, but as this guessing by this topological partition coupling is the M commercial, which appears from this one and security. So this is the non-invertible fusion that we expect for the TSUM theory. There's another fusion that's sort of neat and which will have a really nice string theoretic interpretation, which is if you now take the conjugate of this, you take the fusion, in fact it becomes not trivial, but actually what we'll call a condensation defect for the one-form symmetry. So this is a two-dimensional defect, and it's just given in terms of this background for the one-form symmetry. And it's a condensation defect. We'll look at. So the question is, how do I see holographically these kind of fusions in this Cumrun Vafa? So I was telling you for the last 10 minutes, well, what we need is the symmetry of T, and that's basically all the topological couplings in the bulk supergravity. So here you'll see this is very similar to the couplings you have in ABS 5 times the side, but then there's also the zero form, and it's sort of conjugate, and then there are these anomaly induced couplings. So basically, if you have the symmetry of T, we can just roll with it, write down Gauss-Low constraints, generalizing essentially what Witten did, and then Berloff more extended, including all these anomaly couplings, and we get also these non-invertibles. So that's sort of a very constructive way of getting it done. Yeah, I'll finish, but I will take 2 more minutes because I'll basically show you some pictures about how non-invertible symmetries will come from there. So there's a calculation based on just supergravity that we can perform and show that there are these defects. What's actually much sort of more surprising and maybe sort of more interesting in the long run is there's an alternative way of thinking about symmetries in these holographic setups. So the observation here is if you actually place branes in the near horizon region, so you basically put them towards to the boundary, then they act as symmetry generators. So in fact, what happens is those at the boundary are going to infinity. The tension of these branes basically blows up, and so in this effective action, the dBi, the kinetic terms all decouple, and all that's left is essentially topological couplings. And so what we actually obtain is a picture of placing branes in these holographic setups gives us symmetry generators. In the Cumrun-Vafa setup, what this means is if you place D5 branes in this background, and background is 3 times n3, they actually should give rise to now 3-dimensional, meaning generators of zero-form symmetries. And if we look at sort of the D5 brane action in the limit, it has exactly sort of the coupling C3 that comes from the R form, some gauge fields, and coupling to basically this dB1, which is related to in fact the B2 background field for the one-form symmetry. So the question is, if I take out this kind of brane action and I construct a topological this and fuse two of these, what happens? Again, theoretically, you can just calculate this like in the KOZ papers, and we will find sort of the correct thing. The surprising thing is if you look just strictly think about stacking 2 D5 branes, you actually get naively a U2 non-abelian engaged. That would actually be the wrong result. So what happens here is sort of a really cute thing. Namely, if you have these 2 D5s in this particular background, there's actually also beta flux transfers on the S2. And so what these 2 D5s do is actually, thanks to this Myers effect, they don't just become a U2 non-abelian theory, they actually become a single D7 brane. So again, an abelian theory with some flux. And in fact, right now, what this sort of theory is precisely this theory here. And what it reproduces exactly the fusion of these non-invertible defects. So that's basically saying Myers effect of branes gives rise to this fusion of the defects in the holographic system. If we take now sort of and run with this idea, then the D5s for these generators for these D5s here were generators for the zero-form symmetry. Can also look at the D5 bar fusion, and in fact that should give rise to the condensation defect for one-form symmetry. And in fact that has to essentially correspond to now 2 D5, D5 anti-D5 not annihilating, but actually resulting in some non-trivial tachyon condensate. So in fact these condensation defects really coming from condensation of tachyon and string theory. Okay, so this idea has actually now the branes in these kind of setups should generate symmetries, and in particular also non-invertible symmetries and their fusion, I think has got really a lot of application in holography, but also in geometric engineering, like okay, so one final thing is we can now also ask, does string theory give us a way of now characterizing how these non-invertible symmetries act on the actual charged objects? And in fact, here the sort of another very radial kind of effect comes into play, namely the charged objects are essentially the Toft lines in the PSUM theory. They are D3s that stretch radially out and wrap in S2 and S1 in space-time. And now we can ask how does actually this non-invertible D5 defect act on them. And what happens is if you pass them through, they undergo a Hanani-Witten transition. So it's sort of the picture here, but basically it's probably better to just look at this figure. You have the D3 and a D5, they give rise to the Toft loop. This is a non-invertible defect. And as you now move the D3 through the D5, in fact, there's an F1 string that stretches between these. So in fact, the Hanani-Witten effect precisely mimics what you expect from the field theory, that there's now some kind of disorder operator after you pass this Toft loop through the non-invertible. So string theory seems to have known about all these non-invertible things. Okay, so let me finish. So I think generalized symmetries higher form, higher group, non-invertibles, higher categories certainly are ubiquitous in quantum field theory. There are a lot of things to be learned. I'll just leave this line here. One thing that I think is probably really nice to see is particular line of also at the end of it, how these non-invertibles actually act on physical objects and whether they can actually constrain, for example, things like asymptotic rows of states, what you studied and what you studied in language. So happy birthday. This is, again, I think my photo taking skills are really not particularly good, because the other photos from the other speakers are much clearer. Here's your picture. And many happy returns. The cakes for these 17, 18 are coming. So thank you very much.
Thank you, Sakura, for wonderful talk. Any questions for Sakura?
So what is the relation between the ARIA part where you discuss the fusion, higher fusion category, etc., and then the latter part where you discuss the symmetry TFT?
Because so the relation is that, of course, the symmetry can. So basically, these type of things will also form. I mean, non-invertible things form these some higher fusion category. So
I mean,
what I was talking about here, essentially, when you have this type of structure, so you have all these different symmetry categories related by gaugings, there's essentially a SIM-TFT, and Matthew will call it some Drinfeld center of that higher fusion category that should now characterize, and we can put it into the standard picture. So there's this here. And I can put boundary conditions on it, and you get then all these different mobile forms.
I see. So it's some sort of a reduced information in a sense, or
Like the information you want if you're looking at an actual physical quality. But the point is that these come from some, deep dimension category. Plus conclusions.
Any other questions?
So when you showed us the sandwich, why do you actually need to have that sandwich? Can it be like one single thing?
Why can't you have open sandwich?
So Dan and Greg and Hanson, they wrote this paper, they had a sandwich, and then they had an open sandwich, and they called it the quiche, which I think people, which is not half sandwich. So you can of course open it, you can have just, in fact, this could also be a trivial along with it, right? But
it's like a simplified assumption. I mean, like the symmetry. So symmetry TFT measures the basically the global structure that involves.
So this is basically the superstructures possible. Right? It's like B2D C2. You haven't committed yourself. Right? In holography, if you have this coupling, you haven't committed yourself whether you're looking at SUN superangles, PSUN, SUN mod ZK. Once you put boundary conditions like CB2 is directly, then you have committed yourself. That's basically this putting the left side to the sandwich.
That's you mean anomaly part. The bulk part.
No, in this case, basically, where's the picture of English?
Fine.
So this is basically putting this topological boundary condition,
Okay.
and then you collapse the sandwich, and the interval reduction gives you then the actual theory, T. Right? So this gives you the physical theory upon collapsing of this blue region. And then this gives you the same amount of polyins that sticks around.